But yeah, anyway, we have a few weeks to kind of cover some other material. What we're going to be doing is talking about recurrence relations this week and start into that. And after that, we are going to jump to the graph theory portion of what we're going to cover. So there'll be 6 or 7 weeks of graph theory as well, which we should have time for. So it should be a pretty good mixture. So we're going to start chapter 7 right now. Does anybody have any questions though? There's nothing due today, nothing due this week. The next assignment is due next Thursday, and it's based on the stuff we're going to get into right now. So chapter 7, let me get started on it right here. And as I said, we're going to talk about something called recurrence relations. And so what this is trying to solve counting problems by replacing them with smaller versions of the same problem and then figuring out how to kind of link them up, right? So if I ask you how many bit strings of length 10 have 3 consecutive zeros, we might start by figuring out, well, how many bit strings of length 9 have 3 consecutive zeros, and then use that to help us figure out how many bit strings of length 10 would have 3 consecutive zeros. And we can kind of like reduce this down several steps to a point where, oh, well, now I'm counting bit strings of length 3 that have 3 consecutive zeros, and there's only one of those. And so we can kind of build our way up from there. So let me first just make a definition here, and then we'll obviously get a lot of practice with all of this. Given a sequence, you can view this as a sequence of numbers. Let's just say A0, A1, A2, and so on, and it might go on forever. A recurrence relation expresses a general term or a general value A sub n in terms of the previous values, or I should say previous value or values. It would, there's different kinds of recurrence relations. So how many previous values you use might affect things a little bit. But I'll just say an minus 1, an minus 2, an minus 3, and so on. It's not even clear for sure how many of them there might be. So just as an example, maybe a couple of examples of recurrence relations. So this is where you're expressing the nth term of the sequence in terms of previous terms. Maybe you have something like this, that A sub n equals n times A sub n minus 1, where n is, let's say, greater than or equal to 1. Now, when you do this, when you do something like this, you have to have an initial condition. You have to have like a starting point. So if I write A10 in terms of A9, and then A9 in terms of A8, and A8 in terms of A7, that's fine. But at some point, you got to get to a number that you can actually, get your hands around, a specific number. So maybe I would give you, I'll just add here, with initial condition. We could just call this an initial condition. Let's just say A sub 0 equal to 1. So that's just an example, okay? So what you might realize about this is that actually this recurrence relation just describes the factorials. So A0 is really just 0 factorial. A sub 1, so here, just to add a little add-on here, A sub 0 is 0 factorial, which is 1. A sub 1, according to the formula, is 1 times A sub 0, which would be 1, which is, 1 factorial. And then so on, A sub 2 would be 2 times A sub 1, according to my formula here, and that would be 2 times 1 factorial, which is better known as 2 factorial, and so on, right? So in general, I'll just say dot, 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 okay? So in general, right, a sub n is equal to n factorial for that particular one. One of the things we're going to be learning how to do is figuring out how to solve these recurrence relations. By solve a recurrence relation, I mean take the relation itself, which is what this is, expressing the an value in terms of the previous values, to take that relation itself and use it to somehow come up with an explicit formula for the nth term of the sequence. Okay, so that's actually going to be one of the big things we're going to try to do. Let me give maybe another example that's, you know, a little bit more pertinent to what we, well, factorials are pretty pertinent. We've seen a lot of those, haven't we, in recent times? So we also could write down something like this. I think this one I imagine will look somewhat familiar. Do you remember our good old derangements values? So d sub n, we have an explicit formula for the number of derangements of n objects, but we also have a recurrence relation for it. And, sorry, that should be n minus 1. N minus 1 times d sub n minus 1 plus d sub n minus 2. This is another example of a recurrence relation, and this one came up in the review materials for the exam. I think I did it as a review session problem, just using the formula. So in this case, we used the formula to prove the relation. It's usually the other way around. Usually you're given the relation and you use that to derive a formula, you see, right? So that's another example. And here, you would need to give 2 previous initial values in order to be able to actually work with this recurrence relation. So I would have to give you the values of, I could use D1 and D2 if I wanted to. If I have one object, it's impossible to derange one object. But if I have 2 objects, there's one way to do it. And then you can use those values to figure out D3, D4, D5, and so on. So this is kind of the idea. Or you can go in reverse and take Dn and break it down into smaller values as well. So that is an example of a recurrence relation for the derangements. By the way, the recurrence relations are also not unique. So you can have many of them. You could probably figure out how to make a factorial recurrence relation that describes an in terms of an minus 2 instead of an minus 1. Think about how you might be able to do that. But these are not unique. These are not unique relations by any means. Okay. So the strategy of what we're going to do with this, and I've just given you a couple of examples to kind of get started with so far. I haven't gone into this very deeply at all. Is that to count via recurrence relations. To count via recurrence relations, we apply 2 steps. Okay, there's sort of 2 steps to this. If I want to count things or do combinatorics or do arrangements by using recurrence relations, there's going to be 2 things that we need to be able to do that we're going to learn about in this chapter. One is we need to be able to create the recurrence relation. Create the recurrence relation for what we want to count. So you have to be able to create the recurrence relation, first of all. And then secondly, we need to learn how to actually solve the recurrence relation. Right, we need to actually be able to solve the recurrence relation as well. So we have to create it, and then we have to also be able to solve it. Okay, so both of those tasks will take us the better part of a week to get good with. In fact, there's going to be 2 homework assignments on recurrence relations. One of them is mostly going to be doing problems where you're creating the relations, and the other one is going to be mostly problems where you're solving them. We're actually going to focus more on number 2 first, Number 2 is the more cookbook thing to learn how to do. It's basically, you know, if the relation looks like this, then here's the steps you use to solve it, right? Whereas with creating recurrence relations, that's more of the kind of you know, the creativity part of it. Is where you kind of have to think outside the box, and each problem is a little bit of a new adventure of trying to see how can you describe the thing that you're looking at. So yeah, I think that both of these deserve a fair bit of attention. Let me just give you one example of a number 2 right now, just so we can kind of see one idea for how to do this. So let's imagine, let's try to solve the recurrence relation. So I'm going to give you the relation this time, so I'm going to take care of step 1 for you. You don't even have to do it. And I'm going to use m sub n equals 2 times m sub n minus 1 and then plus 1. With an initial condition, I am going to give you an initial condition here, which is that m1 is equal to 1. Okay, so I would like to show you one way to solve this. And so for the solution, come over here. Okay, so just come over here. Basically what you can do is you can substitute this thing into itself iteratively, like over and over again. So it's really a brute force. There's no big theorem here. Is this more or less you're just going to try to get an explicit formula for the nth term of the sequence by just plugging it into itself. So the first step is to just write it down again. And then what I'm going to do is I'm going to look at the m sub n minus 1. And everywhere I see an n here, I'm just going to now shift it to n minus 1. So m sub n minus 1 would be 2 times m sub n minus 2 plus 1, right? I could just put that in here. So I could just literally put 2 of m n minus 2, and there'll be a plus 1 on that, and then a plus 1 on the end of all of that as well. Okay, and this can be simplified a little bit, although you want to be careful. In fact, maybe what I'll do, I'll simplify it right here. When you're simplifying these, you don't want to simplify them so far that you lose the pattern, because actually the idea here is to look for a pattern that's going to happen. So like instead of taking 2 times 2 and writing it as 4, I'm actually going to leave it as 2 squared, right? Times m sub n minus 2. And then on the end, I have 2 times 1 plus 1. So it's just plus 2 plus 1. Okay, so I've now plugged it into itself once, and that's what I would end up with. Sorry, I'm just going to move this over here like so. Now I'm going to do that again. I'm going to do the same thing again. I have 2 squared, and where I see the m sub n minus 2, I'm going to replace that with 2 times m sub n minus 3 plus 1. And then I'm just going to add the 2 and add the 1. Is everybody following this? You okay? All right, and so then I'm going to clean this one up. So the first part just becomes 2 cubed times m sub n minus 3, and then plus, I guess, 2 squared, which is 4, plus 2 plus 1. Actually, again, probably I shouldn't write 4. Let me just write this as 2 squared. Okay, so it's actually helpful to not simplify it in a case like this. And I keep going like that, right? So the next one, I could go dot, dot, dot at some point once I realize what's going on. What I hopefully will eventually figure out is kind of the general pattern. Eventually, when we get far enough along, this m value will go all the way down to a subscript of 1, because that's where our initial condition came from. So let's see, what would we have at that moment? You just have to kind of look at the form of what you have. In order for this subscript to be a 1, how much do you need to be subtracting from n? N minus 1, right? So, and that amount that you're subtracting is the same as the exponent on the 2. This is why it helps to not have simplified it as you went along. So this is 2 to the n minus 1 times m sub 1. Okay, and then what we see going on to the right are just the lower powers of 2 being added together, right? So 2 to the n minus 2 plus 2 to the n minus 3 plus dot 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 plus 2 plus 1. Okay, and at this point, m sub 1 is equal to 1. I can just plug that in. And all I have is a finite geometric series, right? You guys remember the good old actually, I should put this down as a recall right now because we're going to be needing this. If you add 1 plus x squared plus dot 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 up to x to the n minus 1, there is a formula for this that comes up. It doesn't work all the time, but for most values of x, it will. It's x to the n minus 1 all over x minus 1. Okay. Yeah, if you actually cross multiplied this and multiplied it out, you'd get this numerator here. So it's easy enough to check this. Obviously, when x is equal to 1, this isn't going to make any sense. But in general, it's a good one that we can use. So using the formula here for the finite geometric series. This is just powers of x being added up. So the very last one would be 2 to the n minus 1 all over 2 minus 1. Okay, and so the answer here would be 2 to the n minus 1. I have to leave these pauses so you know what. Is this 2 to the n with 1 subtracted from it, or is the 1 subtracted from the exponent? It's quite challenging to explain that. If you're looking for a nice example of a recurrence relation that fits this one, has anybody heard of, I'm gonna send you home to your computers to Google this one. Have you heard of the Towers of Hanoi? Yeah. Basically, you have a stack of objects, n objects, they're stacked up with, they're different sizes, and the smallest object is on top, and then there's a larger one below it, and then a larger one below that, and below that. And your goal is to move all these objects to a different pile, but you can never put a bigger object on top of a smaller one. So you have 3 piles that you're allowed to make, and the question is, how many moves do you need to transfer one pile to another? And turns out that if there's n objects, it's hard to directly understand that, oh, if I have 5 objects, it's going to take 31 moves. That isn't obvious, but what does become obvious when you really understand how the game works is that the number of moves for 5 objects is just double the number of moves for 4 objects plus 1. So you can get this easier conceptually, and then this derivation that I just did here gives you the explicit formula for the solution to that relation. So it's a famous problem, and I sometimes show the game, but I've realized you can just look this one up. It's so famous. Yeah. So anyway, by the way, I might be going to Hanoi. I have some plans finally to go to Asia this winter. I've never been there, so we'll see if I make it. It's a long trip. I don't like flying. This is so hard to sit on a plane that long, but I might try. What's that? Are you climbing the mountain? Not on this trip, but at some point I would like to do some things like that. Yeah. That's always a good question to ask me. Okay, so that's one way of solving a recurrence relation, is to sort of brute force plugging the relation into itself. Smaller and smaller versions of it getting plugged into itself again and again and again until you have an explicit formula. There's another completely different way to sort of approach step number 2, which is what I'm going to show you next with another very, very famous example of a recurrence relation. Does anybody know any other recurrence relations, by the way? We've done the factorial, we've done the Towers of Hanoi. The Fibonacci numbers. Yes.
There's another Tower of Hanoi, except colors and like 3 stack. So
really?
Yeah.
You have to explain that one to me after class. I don't think I've seen that one with colors. Yeah, I'm not familiar with it, but I totally believe there's like nice variations of these problems. So, but yes, the one I was thinking of is the one that Tanner mentioned, which is the Fibonacci sequence for sure. So let's solve the recurrence relation. Solve the recurrence relation. So probably you all know this one. I'll call it f sub n this time. And this one is equal to f sub n minus 1 plus f sub n minus 2 so the standard way of setting this one up is f of 0 is 0 and then f of 1 is 1. Okay, so I'm sure you've seen this one referred to as the Fibonacci numbers, the Fibonacci sequence. In other words, it has this very famous recurrence relation that goes with it. There are other famous relations, famous sequences that have the same relation but different initial conditions. There's something called the Lucas numbers. I had a student do some research with me once. The Lucas numbers are the exact same relation but with slightly different initial values, and you get some very interesting behaviors out of that. So you can spend a lot of time studying these things. This one is actually best solved not so much by plugging it into itself over and over again, but rather by just guessing the answer, basically guessing at least the form of the answer, and then trying to make it work, which is actually a strategy that you would have seen with something else in your math classes, specifically differential equations. If you have a certain kind of differential equation, you probably learned that, like, if it was a constant coefficient homogeneous differential equation, try e to the rx. Or if it was a Cauchy-Euler differential equation, try x to the r. And there's different forms like that, and you just plug them in and try to solve for r. Right? That's kind of the way that those go. So we're going to use that same strategy here, and when we get to the sort of the broader principles of solving the recurrence relations, it is going to remind you of how you learned how to solve differential equations. And it's very cookbook and very technical. I personally prefer the first part, like creating the recurrence relations. That's kind of where the fun resides. But I'm going to show you both sides of this coin. Okay, so for this is sorry, I should say this is for n greater than or equal to 2 for that particular equation there. So we're going to try to solve this explicitly for the nth Fibonacci number, right? So for the solution here, we are going to guess the solution. So I always hate that. I'm always like, I went to school for all these years so I could guess the answer. Yeah, I guess that's it. We guess the solution, f sub n, and here's what we're going to do. We're going to guess that the correct formula is just a power of q, where q is to be determined, right? So we're going to see whether or not we can make a solution with this form. Now, I'm pulling this out of the sky right now. You have no reason to believe. Why didn't so I've created a power function of n. Why wasn't it a polynomial? Why wasn't it a logarithm? Why wasn't it a rational function, right? So you have to trust that in the theory, in a theory like this, people way smarter than me and way before me came along and figured out what's going to work. And now I'm just the messenger. So anyway, turns out this is what's going to work here. We're going to plug that into our recurrence relation. So substitute. Let's just see how this shakes out. So we're going to get q to the n equals q to the n minus 1 plus q to the n minus 2. And like I said, we're going to try to solve for q. As you can see, we can cancel q's from every term here. And if I cancel, I'm just going to cancel. Then we're going to get q plus 1. So q squared is equal to q plus 1. And that's just a quadratic equation for Q that we should be able to find the roots of, yeah? So, let's just rewrite it as the standard form of a quadratic. So Q squared minus Q minus 1 equals 0. Yeah, did I mess
Sorry,
up?
you lost me.
Oh.
How did we go from Qn -1, Qn -2 to
To
that?
this?
Yeah,
Oh, so I see factors of Q that are common everywhere. So if this was Q to the 10th equals Q to
Yeah.
the 9th plus Q to the 8th. I'm just saying, let's divide
I got you.
everybody by
Okay.
Q to the 8th.
okay, that's what you meant by cancel, gotcha.
Yeah, sorry, I was a little too brief. So cancel, actually what we're canceling, if we want to be more precise, we're canceling Q to the N minus 2. Actually, the thing we're canceling. So is that okay?
Yeah, thank you.
Yeah, okay, great. So we get this quadratic equation essentially, and now I'm going to use a quadratic formula to find the roots of that. Okay, so using the quadratic formula, we're going to solve for Q. We're going to get 1 plus or minus the square root of, so it's B squared minus 4AC all over 2A. So 1 plus or minus 1 squared minus 4AC, but 4AC is -4. So it becomes plus 4 all over 2. I hope I wasn't mumbling too much. This is just the B squared minus 4AC underneath that radical. And this can be simplified to 1 plus or minus the square root of 5 all over 2. So we actually end up with 2 values of Q. And actually, one of them is negative. If you think about it, one of them is positive and one of them is negative. Obviously, neither one of these is correct by itself. I mean, these aren't even whole numbers, right? So the upshot is this cannot be the correct form of the Fibonacci numbers. However, what we can do is we can take all possible linear combinations of these two solutions to see whether we can derive a solution that involves only whole number integers. So what I mean by that is, you know, we refine our guess to the form. I'm going to give you a new and improved form of the guess for this thing, which is that we're going to guess that f sub n is going to have the form of some constant, I'll call it C1, times my first value of Q, 1 plus the square root of 5 all over 2 to the n, and then plus C2 times the quantity 1 minus the square root of 5 all over 2 to the n. Okay, so we've taken the 2 individual roots and we've kind of built the most general expression that we could out of the 2 terms that we came up with. And to see whether this is solvable for the Fibonacci number Fn, we are going to try and find out what the constants are by using the initial conditions. So you have to use these initial conditions, and you'll notice that I have 2 initial conditions here, which is no coincidence. It's because this ended up being a quadratic equation. And that is because the nth term relied on the 2 terms before it. Did you notice that? Like this one, I only had 1 initial condition.
Yeah.
And now this one, I have 2. So the number of initial conditions is somehow that is required. The number of required initial conditions is somehow linked up with like how far back the recurrence relation goes from the nth term back to a certain number of previous terms. Yeah, so anyway, I'm gonna just try to plug in f of 0, right? We know that it equals 0. And if I put in 0 here for n, well, when we raise something to the n, when we raise something to the 0th power, we get 1. And so you get C1 plus C2 equals 0. And then when we plug in 1, we'll get another equation. So F1, which is equal to 1. This is C1 times the quantity 1 plus the square root of 5 all over 2 plus C2 times 1 minus the square root of 5 all over 2. And I have, you know, 2 equations and 2 unknowns here. It's basically what we're looking at. Making some sense? Doing okay? All right, so let's see. Probably the way I would handle this is, well, the way I would handle this is I teach linear algebra, I put it in a matrix. But we don't need to do that. This is easy enough. I'm just gonna replace C2 with the negative of C1 and then factor that out. So I'm just going to replace right here, I'm just gonna make a little note. C2 is being replaced with negative of C1. And so for this next step, then I get C1 times 1 plus the square root of 5 all over 2. And then minus the quantity 1 minus the square root of 5 all over 2. That's gonna look like that. And let's just, I guess I have to keep going over here. Let's just clean up this part that's in these brackets, okay? So I can make a denominator of 2 just to make it simple for myself. And in the numerator, I have 1 plus radical 5, but I'm also subtracting 1 minus radical 5. So I believe that that's coming out to 2 radical 5, I'm not mistaken. This is all still equal to 1. And so this is just the square root of 5 times C1. Okay, so from there, we find out that C1 is 1 over the square root of 5. And C2 is negative of 1 over the square root of 5. Okay, so those are my constants, and I can now plug those back into my form for the nth Fibonacci number. And so thus, f sub n would be, this is so remarkable to me. These are just whole numbers, and yet the answers for expressing them explicitly involve the square root of 5. So 1 over the square root of 5 times the quantity 1 plus the square root of 5 all over 2 to the nth. And C2 is negative of that. So minus 1 over the square root of 5 times the quantity 1 minus the square root of 5 all over 2 to the n. And this would be it. And what's amazing about it is that this is always going to come out to be a whole number. If you take powers, any powers you want, nth powers of those weird expressions, those square roots all disappear when you clean those up and simplify them. It's quite unexpected. This should be quite unexpected. All right. Okay. Does that make sense to everybody? I've kind of shown you 2 things. One is the sort of back substitution into itself. This is this sort of iterative reapplying the smaller versions of the recurrence relation into itself over and over again. And now here's another one where, the trick here is to just kind of guess a solution. Of course, there's lots of holes that I need to fill in. How did I know to guess this, you know, and stuff like that? Or how do I know whether I should guess anything, or should I use the iterative substitution method? Or could there be another method? There's a lot of things we still have to talk about. But before I leave the Fibonacci numbers behind, that would be so horrible, wouldn't it, to just like talk about the Fibonacci numbers for 10 minutes, and this class would be the place you should talk about them a lot. I wanted to say a little bit more about, well, this gets into proofs involving recurrence relations, because a lot of times you need to use induction. You won't be surprised at that, because of course, after all, recurrence relations are describing like the nth version of some formula in terms of the n minus first version, or the n minus second version in this case as well. So, you know, that kind of hints at the idea that induction is often used for to prove things, that you can sort of assume that things work nicely for the smaller versions of what you're proving, and then use that to prove the current version. So just as a little bit of a remark here, and then I'm gonna do an example of it using the Fibonacci numbers. Because of the nature, right? Because of the nature of recurrence relations, proofs involving them often use induction. They often use induction. And so that's something to kind of keep in mind. So let me just give you one example of that, okay? I'll just show you like how you would maybe use this for one example. So let's prove that f1 squared plus f2 squared plus f3 squared and dot 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 plus fn squared is equal to fn times fn plus 1 for all positive integers n. For all positive integers n. Okay, so yeah, this is a equation that involves squaring all these Fibonacci numbers and adding them up. And it turns out it's equal to the product of two other Fibonacci numbers. And this is another hint as to using induction being relevant, because you're proving a statement. You're not just proving one statement, you're proving infinitely many of them, right? One for every value of n equals 1, n equals 2, n equals 3, and these are integer values. If this said real numbers here, or if it said rational numbers or something else, you wouldn't be thinking about using induction. But when you're dealing with whole numbers, particularly positive whole numbers like this, it totally makes sense to do that. Okay, so have you guys done induction lately, or I know you've done it. I don't know what classes, I'm trying to think what other classes I teach where I have to use induction. It's not too many times I use it, but it's a very powerful technique. Usually there's two parts to this, and the first part is the induction base case. So there's something called, I usually just call it a base to kind of start from. And the base case is to just sort of prove the smallest value of n. So if we're dealing with positive integers, that would be n equals 1. And usually this is not difficult. This is generally the easier part of the process. You just plug in the n equals 1 version of what you have. So the left side, if I stop at n equals 1, I only have one term. And you're just comparing that with the right-hand side for n equals 1, which is f of 1 times f of 2. And the question is that true? So I have to be a little careful. I did something that I generally don't like to see, which is I wrote down what I'm trying to prove with an equal sign as the first thing. Technically, I need to check that, but obviously I know that f1 is 1 and then f2 is also 1. And so we can check that off really quickly. So by the way, f2 is equal to 1, right? So if f of 0 is 0 and f of 1 is 1, then f of 2 would just be the sum of those two previous numbers, which is also 1. So this checks out. Sometimes you need more than one base case. And it's not always clear how many base cases you really need to prove on a particular relation until you get a little deeper into it. But I'm going to stop with just one base case for now. And let's see when we do the induction step, how many previous versions back of the equation that we actually need to use. That's actually what I'm going to do. Okay. So let's do this. So for those of you who nodded that you've seen the induction, or you've done the induction, which is probably all of you, do you generally assume this statement as written and then try to prove sort of the next case of it? Or do you tend to prove or assume sort of the previous version of the statement and then prove this one as it's stated here?
Depends.
It depends on the professor or on the question.
Or sometimes like if you're writing a lot of n+1s, yeah.
Well, Dr. C did in -1 a lot of times, but he also said there's sometimes it's better to do, depending on the problem.
It depends on the problem. It actually does depend on the problem. And I find it depends on the person and all of that stuff too. I generally like to assume, excuse me, I generally like to assume the previous version of the statement. So that what I'm actually proving is what it had asked me to prove in the first place. So what I would probably do here, guys, is assume the n-1 version. Now, if this is not your favorite way to set this up, as I said, it's not the only way to do it. You could assume the version for n and go to the next one. But the n-1 version of this statement would just be, that you're adding up the squares of the Fibonacci numbers up to the square of fn-1. What I'm doing right now, guys, is everywhere I see an n, I'm changing it to n-1. Okay, and I'm gonna assume this, and now I'm gonna try to prove exactly what was written in the question. You with me? Okay, I like to set it up that way. So then, if I take f of n1 squared plus f of n2 squared, I'm literally going to start with this side here. And let's try to really make sure that the proof writing on this is good. When I do this, I have to just remind myself not to write anything over here underneath the left side. So where proofs get muddled is when you're kind of working on both sides of the equal sign at the same time. I'm like, well, what just happened? It's easier if you just kind of go boom, 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 boom in one single column. And be sure to put equal signs between your steps as well. So I'm being a little fussy, but that's what we should do. So the left side here, I'm hoping to end up with this. That's the other thing. Don't write this down yet. Okay, what we want to do here is figure out how to use the assumption. And do you see how to use it? This left side is actually part of what you have at the starting point here. So can't I just, maybe if it helps us, we can actually write just that much down with some parentheses around it. Okay, I'm just trying to be real careful here because it's easy to skip steps and just think this is something we don't need to spell out so carefully, but let's try to write it carefully. I'm gonna use those parentheses, and then I have got in the parentheses something I can replace with fn-1 times fn, and then plus fn squared. Okay. Any suggestions what I might want to do with this? We ultimately want to end up with this over here, but it may or may not be clear what to do. But we can think about it and spend a minute. What would be the natural thing to maybe do here?
Factor.
Factor it. Even if you don't know exactly where this is headed, just try it, right? There's no harm in trying it. So I'd probably factor the fn. It'll leave me with fn-1 plus fn. Now I am adding together two consecutive Fibonacci numbers. And so that means that the result should be the next Fibonacci number up, which would be the f of n plus 1. That would look just like that. Does that make a little bit of sense? At this point, we might want to look at the.
Since we're assuming that equation is true, couldn't we have just started from that?
You could have just started from this and added the fn squared to both sides.
Yeah.
Absolutely.
Okay.
Yeah, that would have been fine.
Okay.
Yeah, sure. Okay. Other comments, other questions? I like to look at my induction step part and just confirm for myself that I only used the n-1 version because I only assumed the n-1 version here. And what I noticed is, yeah, I only replaced this with this. That was the only place where I didn't go back to sort of subscripts with n-2 on them, for example. So I'm only using the one previous version of the statement. Why is that important? If I had used the two previous versions, what would I have needed to do first? Two base cases, right? And you can always go back if you realize halfway through this part of the proof that, oh, I actually need to do the n-2 version as well. Well, then you can come back here and just check the second case as well. Sometimes if I'm not sure, I'll just rattle off a few of them And just hope it's good enough, and usually it is. You usually don't need that many base cases.
Cause it doesn't hurt to have an extra one. you're not using.
It doesn't. So there was a problem. And I've taught this class a few times, so I kind of remember this. Let me give you one more example of this, and I might actually be doing one of your homework problems for you. So forgive me, I know that you're gonna be really upset with me for that. But I think this might be one of them from the homework. So we could also do this, prove that f sub n is even if and only if 3 divides n. Can I use this notation? This just means divides here. So in other words, that n should be a multiple of 3. Okay, and just as sort of, I guess you could say, a sanity check. If we write down our Fibonacci numbers, so F0 was 0, so this is the 0th one, and then 1, and then 1, and then 2, and then 3, and then 5, and then 8, 13, and 21, and so on. So it should be, 0, 1, 2, 3, this is the 3rd one, right? This is F3, this is F0, this is F6. And you see that the even ones are occurring when the subscript is a multiple of 3. Yeah. Look okay? Yeah, so this is just kind of checking. Actually, if you want, this is kind of your base cases. Just checking the base cases here. Okay. So let's just think about this one for a minute. Let me prove, I have an if and only if, so I do have to prove this in both directions. Let me just set up this backwards for starters. I'm going to do this. So I'm going to assume that 3 divides n. And I would like to show that f sub n is even. So I'm going to point out, of course, that I'm going to write fn in terms of the previous 2 terms. So fn minus 1 plus fn minus 2. Now, what we know is that n minus 1 and n minus 2 will not be multiples of 3. Right, because if n is a multiple of 3, only every 3rd number is a multiple of 3. So 3 does not divide n minus 1, and 3 does not divide n minus 2. So this is what I'm saying, that we are now going to be relying not just on the n minus 1 information, but actually also the n minus 2 information. The fact that 2 numbers ago was not a multiple of 3 as well. So by what we would call strong induction. By strong induction, so strong induction just means that when you're assuming the previous versions of your statement, right, you're allowed to assume as many of those previous versions as you want, not just the immediate predecessor, but all of the earlier terms can be assumed. So by strong induction, which we apply to both of these, we can say that f sub n is, f sub n minus 1, correct? Subscripts, right? F sub n minus 1 is odd, and f sub n minus 2 is odd. Good enough? And so, well, now I'm adding 2 odd numbers together, and so f sub n would be even at that point. So then f sub n is even. And I'll just give the little reason here, since it is the sum of 2 odd numbers. Yeah, so there you go. So, but we are using the statement from 2 values of n ago. So if we were proving this for a base case, I would want to prove it for n equals 0 directly. Well, that's just this. And for n equals 1 directly, which would just be this one, which is you know, f sub one is obviously odd. Okay, does that kind of make sense? All right, so let's go the other direction then. So prove the forward direction here really quick, see how this one would look. Assuming that f sub n is even, I would like to prove that three divides n. I'm actually going to recommend that we do that by way of contrapositive. Okay, so if I'm proving from left to right, I want to conclude that three divides n, but let's assume that three does not divide n. And then try to prove that f sub n would have to be odd in that case. Okay, now, if we think about it, if three doesn't divide n, then would you guys agree with me that three would have to divide one of the two previous numbers? Either n minus one or n. You can't go three numbers in a row without having a multiple of three. So this would mean that either three divides n minus one and does not divide n minus two, or three divides n minus two and does not divide n minus one. It's got to be one way or the other. We don't really know which one it is. Either way, we're going to use the n minus one and n minus two versions of these assumptions to assume. So either way, by the induction assumption, exactly one of f sub n minus one or f sub n minus two is even. One of them is even and the other one is odd. And the other odd. So we do have to write a little bit here, and there would be more than just this way of writing it. You know, you might have your own preference for how you might write that, but this would be a reasonable way to do it. Well, if you add one even number to one odd number, you get an odd number. Okay, so then f sub n is the sum of one even and one odd number. So f sub n is odd. Yeah. I managed to do this right without actually like, you know, using like two Ks or, you know, fn minus one equals, you know, 2l minus one. You could do that if you want to write your odd and even numbers using like actual math expressions. Nothing wrong with that. But here I just chose to keep it kind of in terms of just some language, just some words. You guys feel okay about kind of something like that? Yeah, it's not so
I
bad.
have a question.
Okay, let me see, where am I?
Yeah.
Question, yeah.
Yeah, Marcus,
Oh.
you looking for something? Oh, okay, I was gonna say, you said you would use f of 0 and f of 1,
Yeah,
but isn't, because f of 3 is even, we're gonna use f of 1 and f of 2? You were talking about like kind of your base cases
well,
would be,
this
because
is,
0 is not an odd number.
this is actually for all n greater than or equal to.
Yeah, what I meant
0.
is, because you're saying f of n is even, so our first f of n that's even is f of 3, right?
Then f of n is even.
So our first one's f of 3, that's even?
Actually, f of 0 would be the first
Oh,
even.
well, the next one that we used is previous. So we would be using f of 2 and f of 1, right? Because 1
You
plus
explain f
0,
of 3. Oh, I see.
because
what
you
mean.
said 1 plus 0 and 1 plus 0 is not the sum of two odds, right?
That's right.
Okay,
That's right.
I just want to
So-
make sure I wasn't.
Okay, so since it is the sum of two
Two
odd
odd
numbers, so that would be referring to.
1 and 1, right?
Yeah, so I guess, So I guess here I'm thinking of n being at least 3.
Yeah,
That,
okay.
that's what you're saying?
Yeah,
Yeah.
it was just, it confused me because it's like 0
Okay.
plus 1's not two odd numbers.
I got you, yeah,
Okay.
that's would be the wrong justification for that, yeah,
Okay.
good point. Do you have a question? Yeah. Marcus.
So can you just quickly explain so by strong induction, f of n minus one is odd and f of n minus two is odd?
Sure, so we're assuming that this statement is true for any smaller value than n. So for n minus 1 and for n minus 2 and so on, but specifically for those two. And because 3 is not dividing n minus 1 and not dividing n minus 2, this fails for those previous values of n, which means that this fails for those values as well.
Okay,
And by failing, it means that those are odd instead of even.
okay,
So that's
Yeah.
okay?
yeah.
All right, everybody else okay? So, okay, yeah, the reason I wanted to do this, in part was to show you, that, yeah, sometimes you do have to rely on the previous, more than just one previous version of the statement. In this case, we needed 2 previous versions of the statement to make the argument work. Yeah, okay, super. Yeah, at some point, I have to talk about like this whole cookbook process of like, well, if the equation has this form, then here's what you're gonna guess for the explicit solution to it, and then you do this kind of guessing and checking and plugging in thing. I don't want to do that right now. That's the less interesting part. Let me take a minute just to practice on the creative side of it, which is setting up the relations. Like actually so far, not anything that I've really done in any of these examples is helping us solve counting problems, right? Because the Fibonacci numbers is not like going to help us count how many ways there are to do blah, 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 blah. Let me give you an example of where that would come into play, where we actually can, use recurrence relations to help us. So I'm going to say a bit here, guys, about setting up recurrence relations. So just a little bit here about setting up recurrence relations. So I'm going to give you an example of what one of these things might look like, and I'm going to see what you guys think. Find a recurrence relation. So this will be an example to show you kind of what we're talking about. Find a recurrence relation, and I'll just reiterate one more time. There could be many right answers, right? There can be many recurrence relations that we can use. Find a recurrence relation for the number, and I will call it Z sub n, of bit strings. I guess I haven't talked about these, have I? You all know these are just zeros and ones, strings of zeros and ones. Of length n that contain two consecutive zeros. Okay. So find a recurrence relation for the number of bit strings of length n that contain 2 consecutive zeros in them. So this would be very hard. You could think about whether you could have come up with a formula for Z sub n directly by using, I don't know, stars and bars, use a random permutation or combination, something like that. But you're going to find it very difficult to do that. I might think, well, I could subtract violations, take out the bit strings that don't have 2 consecutive zeros, but then you're going to realize that that's actually just as hard to count as the ones that do have 2 consecutive zeros, right? So this is one of those problems where the subtraction trick isn't going to be all that helpful. I don't really know how to use the stuff we learned before, but if I knew how many bit strings of length n minus 1 had 2 consecutive zeros, I'm just adding one more slot now. And I'm just trying to see, well, will I create like 2 consecutive zeros after I've done that? So let me just put a little bit of an idea here for you guys and see what you guys think. The trick to doing this is to take this one relatively challenging question that we have in front of us and break it down into several easier questions that are framed in non-overlapping cases. Like, so what I mean by that is we can write down some types of bit strings where we fill in some of the string. Even just filling in one number into that string makes it a shorter string of sort of unknown values, right? So that's going to be the idea. So there are types of bit strings in what I'm going to make up into, let me see if I can write this a little nicer, into non-overlapping cases. Okay, so I'm gonna make some cases that hopefully will make things a little easier for myself. For example, would you guys agree that you could have a bit string that starts with a 1? These are just zeros and ones. It could start with a 1, and then after that, I have, n-1 additional slots here. So these are bit strings of length n, and I've put the first slot down already. And then the rest of it's kind of unknown. This is just whatever, ones and zeros. But the point is that if there are going to be 2 consecutive zeros in one of these things, it's going to happen within the n-1 slots. So how many ways would there be to create a string here that has 2 consecutive zeros? It would just be z sub n-1, right?
Yeah.
However many ways there are to put 2 consecutive zeros within the n-1 slots, right? I'm just adding a 1 in front of that, right? So let me just make a comment here, right? There are, we'll just add this on the side. There are z sub n-1 ways to make bit strings of this type with, I'm just gonna write 0, 0 in quotes. Hopefully that's clear enough, the 2 consecutive zeros. Okay, so I'm describing z sub n in terms of the previous value of the z in that sequence, right? So z sub n-1. Does everybody follow this? How this is working? By the way, it's also okay if you wanted to put the 1 on the other end of it. I've seen people do that and it's fine. You can put the fixed value on the far back end and you still have the same idea, right? You still have the n-1 slots with the 2 consecutive zeros. Now, another type of bit string, so that's not everything, right? You could have a bit string that starts with a 0. However, okay, so maybe don't write this down quite yet because I'm gonna erase it in a second. The trouble with this one is that the string of length n-1 might not have 2 consecutive zeros in it, but it might start with a 0 right here. And then when I have this 0 next to it here, I've created a string that now I need to count. So what I'm going to do to avoid that, I am going to avoid that by just I'm going to start with a 0, but then I'm going to put a 1. And that way, if there's going to be 2 consecutive zeros, they have to occur in the n-2 slots over here at the end. Okay, so in this case, there are, oops, I give a little reason here. You guys able to read my writing okay back there? Is this okay? Okay.